Well, thank you for coming. This is almost the last one now. We have one more after this class. So today is our third big review. We are going to be going over Rankine regeneration cycles today. So we will have class today, class on Wednesday, and then for my office hours today, there was
Professor, I think your mic's muted.
Oh, thank you. Thanks very much. So now that hopefully you can hear me, right? So we'll have our third review lecture today. We will have a review lecture on Wednesday. And then by request from office hours today, I will add an extra office hour on Thursday from noon to 1 in this same Zoom link. And you're welcome to come and check that out if you have questions for the exam, which will be this Friday. Now, we've gone over the content of the exam, but we'll have 3 long answer problems and 10 multiple choice, and we will run the exam from 3 p.m. to 7:30 p.m. And I'll also have a Zoom time for questions. So we've done 2 of these course reviews. We're doing the third one today. So the third one here, we will focus on Rankine regeneration cycles. And then next class, I've taken the liberty of choosing a Brayton cycle with sort of all the trimmings. So if someone could volunteer to pick that problem instead of a refrigerator problem, since those are the last ones we did and they're less complicated. So does someone want to volunteer to pick a question from the textbook for problem next class? Anybody? I mean, Jack's gone twice, so maybe someone who's not Jack can volunteer. So we'll ask again at the end of the class, but if we don't have a volunteer, I mean, I don't want to pick a problem because I know what's on the exam. So if I pick something, then it's not a fair thing to do. So I'm going to need a student volunteer, and I will ask again at the end of the class. So that's the end of the material here. So what we're going to do today is go over a Rankine regeneration problem, and we've got a very good one here, one that I think is pretty complicated. But the nice thing about doing a complicated problem is that we're going to see that it is really the same problem as all the other problems that we've done. It's just got more parts to it, right? So this is what this Rankine regeneration cycle looks like. It's got one steam generator, but then it's got 3 turbines. And in between the first and the second turbine, there's some amount of mass that goes through. Oh, let me make sure that this goes on here. So there's some amount of mass that gets diverted between the first turbine and the second turbine. And then there's some other amount of mass that gets diverted between the second turbine and the third turbine, right? So here, right, we're given some information, which I've tried to fill out on a state table. There's 11 different states here. And then it's also, we've seen that, that there are 3 different turbines and 2 different pumps. But I think in this problem, it did get cut off a little bit. So Jack sent me the image of the words in the problem, but then also of the diagram. So this got cut off a bit, but I've seen in the textbook solutions, I found what I think they're asking for. So I didn't look at the solution, but I did look at what they're asking for. I can't find the actual problem, but I think we have enough information to at least try to solve this one. So here they ask us for the heat that goes in per unit mass flowing through the system, right? So that's going to be the heat that goes in at the steam generator. Then they ask us for the thermal efficiency of the cycle. right? Which we know is going to be W dot divided by, or W dot net divided by Q dot in. And then they ask us for how much heat gets rejected at the condenser, right? So if we look at the things that we're going to need to know, right? So here we want Q dot in. We want W dot net, which is going to be the sum of this turbine power plus this pump power plus this pump power. That's part B. And then this part for the condenser over here, we're going to want Q dot out, right? I guess at least in the version of the problem I saw that looks like this, these were both divided by M dot, right? Now, I'm going to suggest to you that it's a good idea to bring colored pencils, right, to your exam, because you might get a problem like this where you've got different amounts of mass going through different parts, right? So I'm going to call the part that gets diverted here Y, right? So that's going to be, oops, we're going to see how well I can trace digitally here, right? So this is Y on this green line here. That's pretty terribly drawn, right? This is going to be Y prime, right? Then that means I'm running out of colors here. I don't know if there's more colors I can pick. Oh, look at this. Look at all the colors, right? So that means through this turbine, right, we're going to have 1 minus Y, right? What else can we pick over? How about orange, right? RIT is orange, right? So here we can go, this is going to be 1 minus Y minus Y prime, right? That's going to be all the way through here, back up, right? And now this is going to be, so this would be, right, if we think about this, so this is now going to be all the mass gets back together over here, right? Because it's going to be 1 minus Y prime, but we're going to add Y prime in here. We're going to add Y over here. So now I need a new color. Let's use light blue. My kids are big Elsa fans, right? So this is, we're going to come through this. This is the total mass flow rate all the way through here and back up here. So this is going to be M dot times 1. So it's pretty complicated. There's lots of different mass flow rates in the problem. I'm not exactly sure how to calculate any of these things yet, right? Although I know when I'm trying to find mass flow rates, what I want to look for is systems that have more than one inlet or more than one outlet, right? So here we have the closed feed water heater and the open feed water heater. Those could be helpful. Or we want to look for places where we know something like a power or a net power or Q dot, right? We don't know any of that here. So I think I'm going to have to not do that to get a mass flow rate, right? The problem does tell us the total mass flow rate here. Although then, at least in the version that I saw, all these other parts are only, heat transfer per mass flow rate coming into the system. Oh, so I do have the second half of the problem here. It's trying to load. So this, I think, just tells us the pressure. Feed water leaves the closed heat at 210. So this is just stuff that was in the image, so that's good. The heat transfer to the working fluid passing through the steam in kilojoules per kilogram, so we got that. And the thermal efficiency, we got that for part B. And the heat transfer from the working fluid passing through the condenser to the cooling water. So that's Q dot out per unit mass. So I think we got all of this. So we're we're kind of in a good point. At least we looked at this. We saw where the mass flow is going. So that's pretty good, right? You might look at this state table and feel like this is not so great. I'm going to assume, because they didn't tell us anything like efficiencies for turbines or pumps. So I'm going to say that these are all isentropic. So I'm going to get rid of the real states. Whoops. It's not as easy as you might. This is, I don't know if you've ever had to like sign your name on, like when you sign for credit card stuff digitally. I suck at this. So you're going to have to bear with me. My lines are nowhere near straight. Right? But I'm going to get rid of... So this problem could be even more complicated if we had real turbines and pumps. But I'm going to get rid of those. Right? So I guess that's better, right? But it's still like we got a lot of work to do here. Right? So the good news here, though, is that, just looking at this, right? So we have enough information to fix state 1 and state 2, right? I guess we could try to draw a TS diagram here too, right? So let's say we had a problem like this. It asked us to draw a TS diagram. So here, right, we'd have our vapor dome. We are going to start, we know that at state 1, going into the steam generator, we have a temperature of, or coming out of the steam generator, we have a temperature of 480 degrees and a pressure of 12 megapascals. So I'm going to draw the pressures that I know. I'm going to say that this is 12 megapascals. I didn't actually check to see if this is above or below the critical pressure, but I'll assume that 12 megapascals goes through the vapor dome there. Then this intermediate pressure, right, we read from the textbook that this is going to be 20 bar or 2 megapascals. So that's some lower pressure over here. This is going to be 2 megapascals. And then this pressure in the condenser, they say, is 6 kilopascals. So it's going to be some low pressure down here, right? 6 kPa. Right? Notice in my state table, I turned all this stuff to bar, right? So you're going to always have to think about what the pressures are, the units for pressure are, right? So I'm going to draw this thing. So I'm going to assume that this is a saturated vapor, or a superheated vapor here at state 1. Now, from state 1 to state 2, we're going to go through an isentropic turbine. This is going to be state 2. Right? I don't know if this should be under the vapor dome or not. I'm just drawing this. This is a sketch. But I might find when I'm fixing states that this is not correct. Right? Oh, I missed a pressure here, right? So this is 2 megapascals. And then I missed this one here, which is 3 bar. Right? So now here, I'm going to come here. This is going to be state 3, and then state 4. So I have 1, 2, 3 turbines. Then I'm going to go through my condenser. I'm just going to assume that this ends at a saturated liquid over here. This is going to be state 5. And then I'm going to go through a pump up here. This is an ideal pump, so it's a vertical line up to state 6. Now, here at state 6, we're adding some heat from the open feed water heater. So I'm going to go like over here maybe, right? And then I'm going to go, so this is going to be state 7. Then I'm going to go through another pump. I'm going to assume this is state 8, right? Now I'm going to heat again at this pressure. Oh, this second pump gets us right up to here, right? So this is state 8. And then from state 8 to state 9, we do some heat through our closed feed water heater. And then we go through our steam generator back to state 1. So this is what the TS diagram looks like. I apologize for, it's not the prettiest diagram. But here you can see all the different processes, and I'm assuming that the turbines and the pumps are all ideal. Right, so now let's go into the problem. Right, now my advice is going to be try to get symbolic solutions first and then worry about fixing states. So the first thing the problem wants us to do is to find Q dot in divided by M dot. So the only place where we're adding heat that we're paying for, so heat that we're like burning fossil fuels to get, right, or running some kind of nuclear reaction, is in this steam generator. So this is going to be from state 9 to state 1. So here, for part A, Q dot in, we're going to assume, whoops, I don't know why that, so for part A, Q dot in, here we're going to assume that this, I don't know why that keeps erasing. So Q dot in is going to be m dot times H out, which is state 1, minus H in, which is state 9. Now to get to that point, yeah, this is getting frustrating, right? So your Q dot is equal to m dot H1 minus H9. Maybe I just won't change. Q dot is equal to, do you know this equation yet? H1 minus H9. But to get here, we've said that this is at steady state. I really don't know what's going on here. Maybe if I'm going to unplug this and plug it back in, and hopefully things get better. Okay, one more time here. Q dot is equal to m dot times H1 minus H9. Right? Now to get here, we had to assume that the system was at steady state, that it was passive, that there was one inlet and one outlet. Notice that because this is an imperial problem, we don't need these GCs in here. And since we don't have the GCs in there, right, it doesn't really matter. It's not going to show up because here we're going to say that we're going to neglect the kinetic and the potential energies, right? So here we know that Q dot is equal to m dot times H1 minus H9, right? But the problem actually wants Q dot divided by m dot, which is just going to be equal to H1 minus H9, or H out minus H in. Right, so that's part A. But unfortunately, I don't know any of these pieces of information yet. Right? Although I can see that I can fix state 1 because I know the temperature and the pressure. And if I'm not inside the vapor dome, then I can fix the state. Right? Now part B wants the thermal efficiency. Now thermal efficiency is going to be W dot net divided by Q dot in. So W dot net, right? So here I know that my turbine powers are going to be positive. So W dot T1 plus W dot T2 plus W dot T3. Now I have two pumps and they're both going to be negative, but I still add them on the top because I'm going to use the first law to get these expressions. So this is going to be W dot P1 plus W dot P2, right? And then I'm going to divide all of this by Q dot in. Right? Now I'm going to take each of these things. I know that for a turbine, if I can make the assumptions that it's at steady state, adiabatic, one inlet, one outlet, and I can neglect kinetic and potential energy, I know that for any generic turbine, I'm going to get m dot times H in minus H out. But here the mass flow rates are all different, right? So here, for my thermal efficiency, I'm going to get m dot of T1 times, if I go up to my first turbine, this is going to be, this is going to be H1 minus H2. It's in minus out, right? So this is going to be H1 minus H2 m plus m dot T2 times H2 minus H3 plus m dot T3, which is going to be H3 minus H4, plus now my pumps, m dot P1 times the pump inlet is 5 and 6, and then the next one is 7 and 8. So this is going to be H5 minus H6 plus m dot P2 H7 minus H8. Right? All of this gets divided by m dot total, right? Because the q dot in was m dot total, and that's going to be H1 minus H9. Right? So to do this, we're going to have to figure out the mass flow rate through each of these other components as a fraction of our total mass flow rate, because I want to get m dot total times m dot total, and then so I can cancel it out. Right? So this is going to be m dot total divided by m dot total. And now my first turbine is going to be all of the mass, right? So all of the mass goes through this turbine. So this is going to be 1 times H1 minus H2. My second turbine is going to have 1 minus Y times H2 minus H3. My third turbine is going to be 1 minus Y minus Y prime H3 minus H4. Now my first pump, right, I go back to my picture, right, and look at my colored pencils. This is also 1 minus Y prime for the first pump. And the second pump is the total mass flow rate. So this is going to be plus 1 minus Y prime times that first pump is H5 minus H6 plus, now this is also going to be 1 multiplied by H7 minus H8, and then all of this is going to get divided by H1 minus H9. Oh, right? It's a lot of effort, but we systematically did this. We see that we don't know H1, we don't know H2, we don't know Y, we don't know H2, we don't know H3, we don't know Y, we don't know Y prime, we don't know H3. Like, you get the picture, right? We got one equation and a lot of things that we don't know. But if we could fix all the states and then hopefully do some first law analyses and get Y and Y prime, then we could find this thermal efficiency. Part C, this is again a heat transfer question. So it wants us to figure out how much heat gets rejected by this condenser. So again, we can do a first law analysis on a condenser. We're going to assume that it's at steady state, that it's passive, one inlet, one outlet, and we're going to neglect changes in kinetic energy and potential energy. And this Q dot out divided by m dot total is going to be, it's not just going to be delta H here, because we only have 1 minus Y prime going through this condenser, right? So there's going to be 1 minus Y prime times, when we look at the condenser, right, it's going to be H out minus H in. So it's got to be H5 minus H4. So the good news is that we have now got symbolic solutions for all of our problems, right? A, B, and C. We did the symbolic solution. We demonstrated that we understand how to do heat transfer, how to use the first law. The problem is, we know almost nothing about numerical values that we can put into this particular problem, right? So I'm going to go through just conceptually how we're going to fix the states, right? So here, I think, because we know the temperature and the pressure here, I'm going to assume that this is a superheated vapor. So I would look in the superheated vapor tables, go to 120 bar or 12 megapascals, and make sure that this is above Tsat for this pressure. But I'm pretty sure that it is. And then I would get H1 and I would get S1. Then what I would do is I would see that S2S is equal to S1. So then I would interpolate and I would find my interpolation factor and I would get S. And then once I did that, I would come back over here and I would get H. I would see, I guess here while we're interpolating, we have to see basically is S2S, is it greater than Sg at this intermediate pressure? And then it's still superheated vapor. Or is it less than Sg and then it's a two-phase mixture? So that'll tell us what table to look at. Once we do that, then we'll find H. And once we know H, we can also go over here and find the temperature. Here, I don't know if I'm going to find X or not, because I don't know if this is going to be, I don't know if this is going to be under the vapor dome or not. Right? Now, again, I'm going to see here the same thing at state 3. So because all of these turbines are ideal, S3 is also equal to S1. And then I'm going to see is S3 divided or greater than Sg at the given pressure of 3 bar, right? And then I'm going to go through here and do the same thing. Is it two-phase or not? Then I'm going to go through the next turbine, right? So this was through the first turbine, through the second turbine. We do this again. So if this was if this was an exam, a lot of this state table would be filled in and you'd be given the opportunity to fill in part of the state table to show that you understand how to do this. I wouldn't necessarily make you do all 3 of these things in a row because all 3 of these states basically you find the same way. So S4, is this bigger than Sg or is it two-phase? I don't know, right? So here I'd figure out, is there a value of X? But because I know S and I know the pressure, then I can find H and I can find the temperature. So that's how I get to the end here of the turbines. Now, I'm going to say that the condenser, the job of the condenser is, so here, when I go from state 4 to state 5, I'm going to assume that the pressure drop is equal to 0 here, right? So that means P5 is equal to P4. So now as I go down here, P5 is also going to be 0.06, right? Or what was it, 6 kilopascals. And then because this is, I'm going to assume it's a condenser, right? So I'm going to assume we're only going to reject as much heat as the minimum amount of heat that we want, right? We're going to do this till this becomes a liquid. So now I know that this means X is equal to 0. And that means that this is going to be HF. And this is going to be SF. Right? And this is going to be Tsat. So now we go through this first pump. So as I go through this first pump, I know that S6S is going to be equal to S5, which I know, and I know that this pressure, so how do I find this pressure? Right? So we're going to want to make this pump so that it increases the pressure of this liquid to the same pressure as we have here at state 3. I want all of these inlets to be at the same pressure. So this is going to be equal to P3, and this here, state 11, is also going to be equal to P3. If we didn't have that, if one of these came in at a pressure that was too high or too low, then we might get pressure going in a direction that we don't, or we might get flow going in a direction we don't want it to go. So we want all of these inlets and outlets to be at the same pressure, right? That's why we have this trap here. This trap is kind of the same as the valve that you would see in a refrigeration cycle. Its job is to drop the pressure here from state 10 to state 11. So the pressure drops, but the enthalpy stays the same. So here at P6, we're going to have the same pressure as P3. So here this is going to be equal to P3. And then we know the pressure and we know the specific entropy, which means we can fix the state. We can see if we have some sort of two-phase mixture here, right? So here I don't know this, but I can find it, and then I'll be able to find the temperature. Now, state 7, I don't know this yet. I'm going to have to do the first law, potentially, and figure out what's going on here at state 7. Although, actually, we don't have to do that, because here it tells us, so this I missed when I was writing stuff down, it tells us as we come out of this open heater, we have a saturated liquid. So state 7 is going to be quality is equal to 0. We also know that state 7 is at P3. So here, I know in this case that this is going to be, so this is going to be HF for this pressure, and I know that this is going to be SF for this pressure, and this is going to be Tsat for that pressure. So now as I go between state 7 and state 8, now what I do is I increase my pressure. So now again, we want the pressure coming in here. Oh no, so this is a closed feed water heater. So I want the pressure here at state 8 to be the same as the pressure at state 9. I'm going to assume that there's no pressure drop here, but I don't need for this pressure here to be the same as the pressure at state 2. But they've told me here that this pressure is 2 megapascals. So I would have to go through and look, but I think that this means that the pressure on the closed side, on the internal side, is also going to be, oh no, here. So here it tells us that state 9, this is going to be at 12 megapascals, right? So we know that there's no pressure drop between 8 and 9. So then state 8 is also at 12 megapascals. So state 8 is going to be at 120 bar or 12 megapascals. I know that here, because we went through this isentropic pump to get here, so S8S is equal to S7, which means that once I have this and the pressure, then I can go back and I can find H and I can find the temperature. State 9, I have the temperature and the pressure, because here, when we go through here, this is, I would want to check, but my guess is that this is going to still be a subcooled liquid because we know the temperature and the pressure. So here, I'm going to assume that this is going to be a subcooled liquid. So here, I would say that this is going to be HF for T is equal to T9, which is 210 degrees Celsius, right? And if I wanted to, I could also get S9 here as well. So this is not too bad. I mean, obviously this would take some time as you're doing the math, but we've gone through the first 9 states. And so far, we've been able to fix all of these states. This one I was thinking I might have to use the first law for, but they actually told me that the quality was equal to 0 there. So now what happens at state 10 and state 11? So again, state 10, this pressure has to stay the same as we go through here. It tells us this is 2 megapascals. And we're also told that this is a saturated liquid. So state 10 is going to be quality of 0, and it's going to be 2 megapascals, right? Or 20 bar, right? So now this is going to be HF for 20 bar, right? And this is going to be SF for the same. And here this is going to be Tsat. Now as I go between state 10 and state 11, I go through this trap, right? The trap is like a valve, maybe a check valve, or it's like this kind of, like we saw in the refrigerator, we had this isenthalpic valve, right? It's basically we get this pressure drop, but we don't get a change in the enthalpy, right? So this is going to be isenthalpic. So delta H is equal to 0. So H11 is equal to H10. So now I do this, and I know that this is going to be equal to H10. So now I can go back to all of these equations, right? Now I know all the H's. So H1, H2, H3, I know H4, H5, 6, 7, 8, right? 1 and 9. I know H5. I know H4. And over here, I know H1 and H9. So that means I can already answer part A, right? Because this was only dependent on these 2 enthalpies. But I can't answer these other parts because I don't know Y and I don't know Y prime, right? And over here, I need both of those things too. So now, what do I do to get those mass flow rates, right? So here, I'm going to see if I can get us another page here. Oops. So now over here, how do I find Y and Y prime? Right? So if I'm trying to find a mass flow rate, there's a couple different options I can use. Right? So I can use something like the area times the velocity divided by the specific volume. Or I can look for a place where maybe I know a Q dot or a W dot, or maybe a W dot net, right? Or I can try to find a component that has more than one inlet and or more than one outlet. So in this particular problem, we don't have any place where we know the cross-sectional area and the velocity, right? I don't know any place where I'm trying to find power or heat transfer rate, but I do have 2 components where I have more than one inlet and more than one outlet. So here I have a closed feed water heater, and I have an open feed water heater. Oh, I keep wanting to put a W for water, right? And, hopefully this is good, right? Because here I have 2 different unknowns. And when I do the first law on these 2 components, I'll have 2 equations. So hopefully that'll give me enough equations to solve this problem, and I won't introduce another unknown. So first, let's do the first law. Well, I guess we can choose, right? And the good news is if you don't pick the right one, you just do the other one and get the full system of equations before you start solving things. But here we have two options, right? So here we could do the first law on the closed feed water heater. The closed feed water heater has some mass flow rate at Y times m dot and some mass flow rate on the other side times just m dot. So this is pretty good because it means that I'm the only unknown that I have in, if I do the closed feed water heater, the only unknown that I have right now is Y. But if I pick the open feed water heater first, you'll see, I know this is another reason why I think different colors are good, because at least if your penmanship is like mine, then it might get a little messy. Oh, it looks like all our all the Q dots that we had that disappeared, apparently they came up to the top of the page here, right? But if we do first law on this open feed water heater, then we're going to have this term, which is going to be y prime. This term is going to be 1 minus y prime. This term, which is going to be y, and then this term, which is just going to be 1. So if I did a first law analysis on the open feed water heater right away, then what would happen is I'm going to see two unknowns in that equation, y and y prime. So I'm going to do this one first, and I'm going to do this one second. Right? So when I do the first law on either one of these systems with more than one inlet and more than one outlet, right? The first law analysis is going to be the same, right? They're going to be steady state. Even though there's heat transfer, we're going to assume that none of that heat escapes to the outside. So both of these are going to be adiabatic. Both of these feed water heaters are going to be passive. They're not one inlet and one outlet. So what? Oh, this should be an out, and this should be an out over here. So what's going to happen for both of these systems? So for both, 0 is going to be the sum of m dot in h in minus the sum of m dot out h out. So here, let's do the open feed water heater. For the open feed water heater, we're going to get 0 is equal to, now what are the inlets? So here I've got y times, or I'm going to have all the mass flow rate times y at this inlet state 2. So for all of these things, I'm going to have m dot total on the outside, y times h2. That's my first inlet, right? I'm going to have another inlet here at state 8. And at state 8, see, I don't have to think about this because I already used my colored pencils. Light blue, this sort of Elsa color here, means the total mass flow rate. So this is just going to be H8. Those are my inlet states. My outlet states is going to be negative m dot times, again, because this is a closed feed water heater, right? So this is still the mass flow rate y times m dot total at state 10. So this is also going to be y times h10 plus, remember this is all going to be times negative 1, so this is going to be plus over here. Now all the mass flow rate comes out here at state 9. So this is going to be H9. Right? Now, I can divide everything here by mass flow rate, and that's going to go away. So then I can collect the terms that are multiplied by y on one side. So here I can have y times H2 minus H10, right? And then I'd have to move the other stuff to the other side, right? So if this term is positive, then this term would have to be negative, right? On the other side of the equation. So this is going to be H9 minus H8. And all this means is that y is going to be equal to H9 minus H8 divided by H2 minus H10. So now I found y, right? But I want to find y prime as well, which means that I have to use this same equation on the closed feed water heater, right? So let's do the closed feed water heater in purple, right? So the closed feed water heater, right? So now 0 is equal to, I got to look at the inlets now. So the one inlet here at state 3 comes in at m dot times y prime. So this is going to be, my inlet terms are all going to be times the total mass flow rate. This is going to be y, and I'm pretty sure we said H3 here. Yeah, I got that right. Now my other inlet is going to be at 1 minus y prime times H6. 1 minus y prime times H6. Right, now this is going to be minus the total mass flow rate times my exits. Now my exit states here is a little bit better. Oh no, there's 3 inlets, right? I forgot one. So I did this one, but there's this other inlet state coming in at state 11 with y times the total mass flow rate. So here I got to amend this. So this is going to be plus y times H11. And that other one should have been y prime. So this is y times H11, and this is y prime times H3. I only have one outlet, so that's going to be the total mass flow rate times H7. So now this is going to be H7. So this is a little bit messy, so I'll clean it up. But first, we'll divide both sides by m dot, so that comes out. Now the terms that I don't know are going to be these y prime terms, right? So here, I'm going to take my time with this so I don't mess it up, right? So 0 is equal to y prime times H3 minus y prime times H6, right? Those are, so now, so I took care of this term. I took care of this part of the term, right? Now I'll say plus 1 minus y times H6, right? So now I got this and this, plus y times H11 minus H7. So I kind of want to isolate for this, right? So I'm going to say, move this to the left-hand side of the equation, y prime multiplied by H6 minus H3, because I moved this over to the other side of the equation, is equal to H6 minus H7, right? So now I got this and I got this, plus y times H11 minus H6, right? Or y prime is going to be equal to H6 minus H7 plus y times H11 minus H6, all divided by H6 minus H3. So now when we go here, right, we take stock, we know all these H values. Y, I wouldn't substitute this equation into there because it's going to get too messy. I'm just going to find this from this equation over here, right? So this gives me y because I knew all these enthalpies, right? And then down here, this gives me y prime. So now I know in these equations, I didn't need this for part A. Part A I did before that. Part B, I still needed y, and I still needed y prime, but now I have all that. And for part C, I also needed y and y prime. Here I would double check just to make sure that this gave me a negative number. I would make sure that y and y prime are both less than 1, and that this term, 1 minus y prime, is not negative. And I would check all of these individual turbines and pumps to make sure that the turbine powers are positive and the pump powers are negative, and this heat transfer in is positive. But if we do all of that, then we would have answers for this problem. Now, will you see this on an exam? Maybe. You could see a problem kind of like this on an exam, but the problem is never going to be this. There's never going to be this much information that you have to answer, right? So you're never going to get to a point where you have to fill in this much of a state table. But I could give you this state table with some of the information on it and ask you to fill in some of it and still ask you to do kind of the first law analysis that you'd see on this particular problem. So it's not unreasonable for you to see a problem that's different than a problem that you've seen like this, right? But if you follow the process that we've been doing, this kind of systematic approach, it doesn't really matter if I show you a problem that you've never seen before, because you'll know how to do it. So does anybody have any questions before we end the lecture for today? Thank you. I'll also need a volunteer for a Brayton cycle problem, which is the problem that we'll do for the next class.
We can probably find one.
Thank you, Matt. I appreciate it. So if you can find us a Brayton cycle problem, preferably a complicated one, right? Like this was complicated too. But the more complicated it is, then, the more you keep me on my toes, right? And the more you get to see as well.
Do you know what chapter it would probably be?
Ooh, that's a good question. I think that this stuff is chapter 8, and gas power plant stuff is chapter 9.
Yeah, chapter 8 and 9 are where at least I'm grabbing all these problems from. I think either the first half of chapter 9 or the second half of chapter 8 has Brayton cycles. Actually, no, it's 9.3 has Brayton cycles. I'm pretty sure. Thank you. Because I was looking for problems earlier today.
Okay.
All right. Thank you very much. And so I will see you again on Wednesday. And then a reminder that I will have extra office hours on Thursday at noon in preparation for the final, which is on Friday. Thanks a lot, everyone.